Hey guys, we're going to do a little video here on the concept of work, power, energy, and we may touch on efficiency as well. So for you to get the most out of this video, get yourself a calculator, a pencil, and some paper, and have, as always, your formula sheet or some kind of reference material. We are going to be dealing with this section of the formula sheet here, and that's essentially this unit that we're on, energy, work, and power. Okay, so we're going to deal today with a definition of those terms and then how to do some basic mathematical operations for them. Okay, so here we go. We're going to start with work. So work is not a typical definition. In physics, we have a physics definition for work, and that basically is work equals force times distance. Okay, so that looks like this. W equals F and then D. Now work is measured in joules, so the units are joules. Force is measured in newtons, and distance is measured in meters. There's your first formula. So technically no work is done unless a force is used to push an object a certain distance. If that object does not move, if distance is 0, then technically no work is done. That's the physics definition. If no force is used and an object is moving, so for example floating through space, then no work is done either. So you need both of these elements for any work to be done. All right, so here's an example. Okay, so for example, you've got a bag of groceries here. We don't know what's in the groceries. And they have a weight of 200 newtons. So if you were to lift them against the force of gravity, you would have to exert a force of 200 newtons, and you have to lift it up a flight of stairs that's 3 meters. So we're going to go up a terribly drawn flight of stairs that's 3 meters. Okay, so our force is 200 newtons. Our distance is 3 meters. And you can easily calculate work. Work equals force times distance. And in this case, that would be 600 joules. Okay, so the force can be exerted upwards. It can be exerted side to side. We could slide those groceries, and if the force needed to slide them was 200, then the work done would be 600 joules again. So that is basically work. The next concept I'm going to do is power. So power includes the concept of time. A more powerful machine can do things more quickly. So power equals work divided by time. So 746 watts equals 1 horsepower. Time is always in seconds, and then work, as we mentioned before, is always in joules for this equation to work out. Okay, next concept really quickly is potential energy. So energy can come in many forms. The law of conservation of energy says you cannot create or destroy energy, but it can flip from one form to the next to the next. For example, light energy can convert into thermal energy. When the sun shines on you, now you feel warm. That's light energy converting into thermal energy. So here's a quick example. We're going to deal with basically two main types of energy in this unit. We're going to focus on potential energy and kinetic energy. And if you think about it like this, if you were to take that bag of groceries, here's a slightly better drawn staircase. and you've got that bag of groceries here, and you carry it up, and now it sits up here. It has more potential energy than it did down here. Okay, we're going to get mathematical about this for a second. So potential energy that's stored in this bag of groceries is equal to its mass times the strength of gravity or acceleration of gravity times the height. Okay, so its mass, let's say it's 5 kg, and it's on planet Earth, so that would be 9.8 meters per second squared, and the height would be 3 meters. 5 times 9.8 times 3 is 147. So 147 joules. That means that the potential energy held in this bag of groceries is now equal to 147 joules. Okay, that's assuming this is our planet Earth. This is 0. So this would be the baseline for which that 3 meters is compared to. Okay, if that bag of groceries was down here at 0, it would have 0 potential energy. It would have no potential energy to fall any further down. Up here it has 147 joules of energy. Now how did it get that amount of energy? Well, we had to put work into it. So work can be converted into various forms of energy. Okay, for example, you could start a fire by rubbing 2 sticks together. You could convert your chemical energy in your body into thermal energy, which would heat up. You could do work on a bag of groceries, you could carry them up the stairs, and that work could then be stored as potential energy. All right, next concept. Kinetic energy. So kinetic energy is equal to 1/2 mv squared. Okay, now remember, all of these equations can be rearranged to find the component that you are missing. So in that last one, we just figured out potential energy. But if you wanted to figure out mass, if you didn't know mass of an object, but you had the potential energy, well then, potential energy divided by acceleration of gravity times height is your mass. So these triangles are useful for figuring out any one component that you don't know. If they're beside each other in the triangle, you multiply them. If they are on top of each other, you divide them. Okay, so going back to this kinetic energy, this one's a little tougher to rearrange, but the rearrangement of these formulas are written right here. So kinetic energy right there, there's the original formula. You can rearrange that formula to isolate V, that's a square root of 2 ke over m, or you can rearrange the formula to find m, and that's 2 ke over v squared. Okay, so kinetic energy is the energy of motion. It's anything that's moving. Anything that's moving has kinetic energy. So if an object is motionless relative to anything else, then we consider it to have 0 kinetic energy. That kinetic energy is equal to 1/2 of its mass times its velocity squared. Let's do a quick example. So if you have, okay, so if you have a car that is 1,000 kilograms. Okay, so I'm gonna do a quick car here. And its mass is 1,000 kg. And it is traveling at, we'll just keep it really easy, 100 meters per second. So velocity has to be in meters per second. Mass needs to be in kilograms, so you need to convert those units to this in order to get joules out here for kinetic energy. All right. So kinetic energy equals 1/2 times 1,000. And we've got multiplied by a velocity of 100. And we're going to square that. So 100 squared times 100 equals 10,000, and then multiplied by half of its mass. So that's 500. So multiply by 500. Okay, so that would be 5 million. And the units are joules. All right, so there's a quick example with kinetic energy. Now remember, we can convert one form of energy to another. So I could put 5 million joules of energy into something and potentially get it going at 100 meters per second. That's if I'm 100% efficient. So that's where efficiency comes into play. I might spend 10 million or even 20 million joules of chemical energy of gasoline, and maybe only 5 million of joules would go into the car and become kinetic energy. So that's a little starting point, guys, with a few quick examples. All right, here's a little bit more on the concept of potential energy converting to kinetic energy and vice versa. If you can imagine the classic basketball on top of the school roof, okay, we're going to assume that this is about 10 meters. Up here, this basketball might have a potential energy of 100 joules. It has the potential to fall 10 meters. And we'd have to calculate its mass times the acceleration of gravity times its height. But we're going to assume that it's 100 joules. Its kinetic energy, if it is not moving at all, its kinetic energy is 0 joules. So it's all the energy is stored in potential energy. As it falls, it increases its kinetic energy and it decreases its potential energy. So here, it might be halfway on the way to converting potential to kinetic. Its potential energy would be about 50 joules because it's fallen half the way, and its kinetic energy would equal 50 joules. It's sped up at this point, and remember, kinetic energy is 1/2 mv squared, so its velocity is increasing, therefore its kinetic energy is increasing. Okay, as it continues, and just before it hits the bottom, it's converted all of its potential energy, so that's now 0, into kinetic energy. And that would be 100. Now that would only be 100 if no energy was lost to thermal, and that's impossible because of friction. So it would have lost a little bit of energy to air friction on the way down. It made some noise, it moved air molecules out of the way, so that maybe it's 90, 95, 98% efficient. So it would lose a few joules to thermal energy on the way down, okay? And that's the concept of efficiency.